The broadcast is now starting. All attendees are in listen-only mode.
Hi everybody, thank you for joining us. My name is Lisa Travers with Alliance Corporation. Today we have an excellent presentation, very technical, to be presented by Bogi Kolbasa from Times Microwave, Lightning Protection and Grounding Solutions for Wireless Networks. I'm going to hand it over to Jerry Besner from Alliance. He's going to give a short presentation and introduction, and then we'll be handing it straight over to Bogi. And Jerry, it's over to you.
Thank you, Lisa. Welcome, everyone. I'd like to take this opportunity to formally introduce Bogi Kolbasa. Bogi, as he likes to be called, has an extensive background and depth of knowledge in grounding and surge protection with many patents in his name. He regularly conducts engineering seminars on topics of lightning protection and grounding solutions for communications networks. And he is currently a member of the IEEE Surge Protection Devices Committee. He's got a lot of work experience associated with 25 years in this industry. Before we get started on his presentation, I'd just like to introduce Alliance to those who don't know the company. Alliance headquarters, as you can see from this picture. One second, I think Lisa's just got to do a change there. Yeah. Thank you, Lisa. Is headquartered in Canada with operations in Canada throughout the Canadian marketplace and in the United States and in Mexico. When we look at the things that we do as a company, we're very active in broadband. We provide microwave backhaul solutions. We do in-building DAS, are very, very strong in supply chain. The wireless infrastructure, we've been in the marketplace for over 20 years doing all types of coaxial cables, and in the recent past we've become leading experts in fiber. When we talk about leading supplier of wireless infrastructure, we consider ourselves a world-class product assortment of various products that we have. We have an extensive inventory in warehouses throughout Canada, throughout the United States, and in Mexico. We have very strong technical expertise with a lot of strong veterans in the industry. We do independent recommendations. We are not tied to any one particular product line. We do pre-post-sales technical supports, including training and the latest techniques of PIM, and as I indicated, warehouses throughout Canada, United States, and Mexico. In addition to our operation as a distributor, we're very proud of the technical services we provide to our customers. We do license applications, network design assistance, path profile, pre-configuration of radios, kitting, tower selection guidance, and we do RMAs on behalf of our various vendors that we represent. So I'd like to thank you for giving us the opportunity to talk to you. I'd like to point out that we do have training videos posted on our website at alliancecom.com, and we do webinars very regularly. So with that, I'd now like to turn this over to Bogi for his expertise on why we're all here for, and that's lighting protection and grounding solutions. Thank you.
Thanks, Jerry. So,
okay, I hope everybody can hear me. Thank you very much for attending our brief session. We'll try to concentrate on the most critical key factors when it comes to lightning protection and grounding solutions, as Jerry mentioned in his kind introduction. My name is Bogi Kolbasa. I'm with Times Microwave Systems. I came from a company called Polyphaser, where I spent many years of my professional life, and transitioning the knowledge base and the background into Times Microwave, pretty much enhancing the LMR cable line, the easy connectors, and some of the grounding solutions and so on. So we felt very strongly about adding this complementary product line. Anyway, to briefly tell you how we are going to handle this one, First of all, we'll describe the nature of lightning in the EMP, electromagnetic pulse event. We'll talk about the statistical nature of the event, then we'll be moving basically to describe the values of currents and voltages associated with this. Finally, we'll be going basically to tower grounding, lightning diverters, then we're going to be going basically inside the shelter, communication shelter, and we finish with samples of specification for the protectors, for all the protectors, and not all, some of the protectors. Because as you will learn from the presentation, regardless if you are IP guy or if you are the RF distribution guy, if you are the service guy, regardless of the industry, some of the principles will apply across the board, from AC, DC, telco, Cat5, Cat6, RF. When it comes to grounding, bonding, and shielding, they could be related. What we'll be talking about right here could be related to almost any area of your expertise. Well, anyway, a few facts about lightning. You know, as I said, it will be purely statistical by nature. At any given point in time, you might have 2,000, 2,500 of the lightning storms happening as we sit right here. And in each one of these events, you might have up to 100 flashes per second or more. During the fair weather weather, basically, when you've got the cosmic rays pounding on all the dirt between ionosphere and Earth, you might have electrical potential of 200 to 500 kilovolts in existence. Most certainly, you're not going to have any current or any H field associated with that, but you know the E field will be hanging up there. And we might have discharges in values of up to 100,000 kiloamperes. I'll show you a statistical distribution of values as we go into the presentation. It is an extremely short event, and each return stroke might last anywhere from 20 to 50 microseconds. And the temperature along the plasma channel as the return stroke is going to take place can reach as high as 20,000 degrees Celsius. So when we hear the sonic boom, this is nothing but the heated air masses along that conductive plasma channel during the return stroke, and a rapid expansion of an air basically is a shock wave, is a sonic boom. Well, here we have an example of aircraft on the takeoff that happened in Kanazawa, Japan, Boeing 747-400 with huge metal skins of aluminum 7071 on takeoff. The huge E field was already in existence, not high enough to start breaking down the dielectric of an air, but all of a sudden you found yourself with a huge mass of aluminum or conductor in that E field, and if you watch this on the super fast cameras, you'll see the nose of the aircraft and the tail started generating step leaders, and basically the aircraft found itself in a field which it shorted. It was fine, just landed in Tokyo. An hour and a half later, everybody was okay. But that simply illustrates in video format what happens basically when the return stroke takes place. Let's remember that energy has to return somewhere. There is no such a thing as lightning avoidance systems, you know, or the fuzzy brushes on the towers, on the cylindrical structure, which they call early streamer emission. I will have some links for you for reading at the end of this presentation. So basically, you'll see some of the questions were pertaining to the static discharge issues, and we'll get there. Here are some illustrations of some of the damage. Well, as I said, the lightning will be purely statistical by nature, and if you take a look at the annual lightning flashes, the distribution of lightning events, it will be very seasonal type issue. So when we are going to winters in the northern hemispheres, you know, the guys in the southern hemisphere are going to be suffering most. And it will be basically changing with the seasonal changes and geographical latitude of where we are located. If you take a look at the equator right here, these guys are just going through the wet season, dry season, year around, and the effects of it are shown right here on this graph. So basically it is statistical by nature. They are not two event alike. Some of them can have 2, 3, 4 return strokes depending on how much charge we have to migrate. And with every stroke, the energy delivered to the communication site or anywhere will be basically directly proportional to the number of return strokes. Here is the United States, and sorry guys, I don't have any Canada map, but you might have some from your global atmospheric bureau showing the exposure. This one is not super duper up to date basically. It was done in 1996 to 2000, but with the weather changes and trends and so on, yeah, you can kind of define some statistical averages. So there are some areas where we are more exposed, some areas where we are less exposed. So how does it happen? What's happening as we are having a jet stream pushing around? We got huge air masses, warm air being sucked up into the upper layers, and as we go up with the warm, moist, humid air, we are going to be experiencing temperature change, gradual cooling off. The higher it goes, the higher it gets sucked, the lower the temperature. So we'll have a natural formation of icicles basically in the whole storm. And I'm not trying to isolate lightning event to just one small cumulus cloud. Usually we are going to have a massive storm or massive jet streams going over areas covering thousands and thousands of square miles or kilometers. So as all the icicles or the particles basically suck up with all the dirt and conductive ions from the surface of the earth, from the water, from the bodies of water, migrate up there. They go through the cooling effect, and this is in constant motion. There is nothing static basically about the event itself. So you are going to have a gradual friction, and you are going to start building up a static and polarize basically the storm. You might have a cloud-to-cloud, infra-cloud type events. At a given point in time, you're going to start establish a dominant charge on the forming a corona. And if the corona is going to be a negative right here, and the amount of charge within the event, I'm saying within the event because we are talking really about the event, not one isolated incident, you are going to start forming a really dominant charge and corona on right here. So at a given point in time, basically, depending on how conductive the air is going to be, you're going to start breaking down. You are just going to keep lowering and lowering the corona, and that breakdown we call basically a step leader. So the step leader is going to be migrating. Remember, the charge has to always return itself somehow. And if the potential and the total amount of charge within the event is high enough, that dielectric breakdown will start occurring slowly. And at a given point in time, okay, even though we don't have a free current flow to return itself from the source, we're going to be rising step potential on the ground. So you might not even have a current flow, but the ground can go to 100 kV, 50 kV, and you are going to see a small streamers blowing basically on the top of the tower, on tree, on high-rise building, and so on. So that opposing streamer is already an indication where the step potential rise will be taking place. And as I say, if you smell ozone, it's usually too late to run. So anyway, sit low at this point. And at a given point in time, you know, basically when the step leader coming down and the opposing streamer will connect, you are going to have basically a free current flow. And typically the impedance of the plasma channel or the conductive channel for the event will be in the range anywhere from 10 to 20 ohms. I don't want to spend too much time on the theory of it. So if you take a look at the typical step leader right here, yeah, the potential will be somewhere in the 10 to 30 kilovolts per meter. And as you have basically the current coming down, E field, and the current in form of that corona coming down, you're going to be looking at the electromagnetic field. You're going to have a E field, you are going to have H field, and you can imagine kind of like a spherical ball coming down on you. And this theory is being applied to the rolling ball theory basically. Many years ago we used to believe that 45-degree cone of protection is going to give us, that tower is going to give us 45-degree cone of protection. Well, then but the questions were, why the heck do we keep losing the side-mounted antenna? So now even NFPA have adopted this rolling ball theory a while ago, and is being quoted by the National Fire Protection Association as well. So how does the current look like? We know that it's going to be short in duration, anywhere from 20 to 30 microseconds. If you take a look at the lightning current signature, you are going to have a couple of values. There will be the rate of rise time, how quickly that current is going to go from 0 to simplify everything. We are marking that to 10% because we are allowing in this case for that 10% basically to be step potential rise where the current doesn't flow yet to 90. So the actual rate of rise time is measured from 10% up to 90% of the current wave shape. So this component will be the frequency component of the event basically. And if you do Fourier and if you take time to frequency conversion, you're going to be looking at lightning event being somewhere from 1 up to 10, 15 megahertz. So for all of us working in the broadband wireless, you know, or the microwave, that's not really that high, but that frequency basically is going to play some tricks on any conductor which will be inductor suspended in the air. The other value for that current will be the pulse duration. How long does it last? So we always measure the pulse duration of the 20 microsecond or 30 or 40 or 50 at the 50% of the rate of the rise time. So this is the RF component, this is the DC component. If you integrate this area under the curve, you see a total amount of charge coming down on you in terms of electromagnetic field. Well, what are the typical values right here? Here is a graph. You could do a bell curve if you want to, but what we did right here are the percentage of specific lightning current values taking place. So at 50%, basically, you might have currents somewhere from 10 kiloamperes up to 50, 60 kiloamperes in that region. There is a small probability of much higher than that events or values taking place, and there is of course distribution on the lower end. So when we design for protection basically of individual RF transmission or AC or DC or Cat5 or whatever we do, we take these statistical values into account as well as the number of feeders coming down, because this current is going to divide itself. So anyway, at 50%, you've got a typical values, and the reason why I like that graph a lot is because you've got many researchers from all over the world, Japan, you've got Human from NASA, you've got Berger from Norway, and so on. And if you take a look, there is a nice statistical tendency. There are some differences based on where it was taken, but there is nice tendency to that graph. When it comes to the rate of rise time, similar situation at 50%, somewhere from 1 microsecond up to 10 microseconds, somewhere in this region. That would be the DIDT, how quickly the current is going to change its ratio from 0 to peak value for simplicity. Now, people are saying, well, I have a coaxial cable, I've got a nice shielding, I capture my grounding kit at the base of the antenna, then another one at the horizontal transition over the cable tray, and then I'm doing my grounding kit basically at the entrance at the bulkhead. Why do I need inline protectors? If you take a look and do a test, basically, everybody knows what their system impedance at the frequency of the radio is going to be. But if you ask people, hey, what's your system impedance at 10 megahertz? I don't know. Or what is going to be at other, at somewhere between the 1 to 10 to 15 megahertz? Nobody really knows that. There are only two ways we get nailed, or equipment gets nailed. If that lightning frequency coming down gets coupled into the center pin through the antenna, because this is not anymore 50 ohm systems, then we are going to have some distribution on the center pin, and we are going to have some distribution on the shield. If you take a look, shield is larger, most certainly, have got much lower impedance. Center conductor is going to be much smaller with much larger impedance, so the center conductor is going to go into attenuation mode, okay? And the longer the cable, the more of an impedance, the lower the rise time and the longer the pulse is going to become. It's not going to diminish anywhere. So on the shorter jumper or whatever, you are going to have pretty much some differential between the shield current and the center pin current. But on the longer run, you are going to have that thing flattening, and you are going to have like a DC pulse arriving right in the front of the diplexer, filter, whatever you've got. So that's basically why we are using inline protectors on the RF coaxial cables. This is a 50 ohm systems, but there is that but. And also you're going to see some propagation delay. So the differential current which is going to arrive at the equipment, if the impedance of the system is low, you're going to go to thermal runaway. You're going to burn everything with that current. If the system impedance is going to be very high, that differential current is going to become a flash over point. You're going to create a flash over voltage, and that's how we get destroyed. Well, getting to the more practical side of this presentation, let's talk about grounding fundamentals for lightning protection. Well, every conductor, and tower will be a conductor with that Ben Franklin rod or the lightning diverter put on the top of the tower. Every conductor, every jumper, every coax cable will be inductor. We don't have these soil clamps to shunt that energy, into the positive environment for that current. So we're going to be experiencing basically huge inductive voltage drop. Remember that the rate of rise time of that current, the DIDT, So if you want to figure out what inductive voltage drop we are going to experience, you just simply take the inductance of the tower or inductance of the cable and factor that into the rate of rise time and peak value of that current to figure out what is going to be the total amount of inductive voltage drop across. So basically every conductor in the air will become an inductor, especially with a DIDT. So if you take a look, there are various ways of calculating inductance. Inductance is treated as electrical value, but this is purely geometry of the conductor we are talking about. And typically if you have a monopole or if you have a three-legged tower, with three-legged or four-legged tower, we are going to have basically some mutual inductance working against us. But in the monopole situation, you can assume that you're going to have anywhere from 0.6 to 0.8 microhenry per meter, which is 0.6 to 0.8 every 3 feet or so. And it's going to be linear by nature. So here is another example of calculating inductance for the three-leg tower, basically, and we are talking about the distance d3. The larger the distance d3 between the tower legs at the bottom, basically the lower the mutual inductance. You can run these calculations based on 2 or 3 parallel type conductors. And now a kind of a graphic representation of what will happen if we're going to have a total mass inductance right here of 40 microhenries with a relatively small 18 kiloamperes peak strike, which has a 2 microsecond rate of rise time. So the DIDT of that strike was in the range of 2 microseconds. We had 18,000 amperes peak, and the inductance of that masked monopole was in the range of 40 microhenries. We are looking at this point at inductive voltage drop calculated basically of 360 kilovolts peak. And the trick right here is that we are going to have a cable tray coming down, we are going to have a grounding kits, we are going to have a coaxial cables which are in the hangers, one from each next to each other. So now we are going to have some mutual inductance as well working between. It is a very complex electrical circuit to analyze actually. But the inductance of the coax shield is going to be drastically different than the inductance of the tower. So we are going to experience different basically inductive voltage drop on the tower as on the cable as on the grounding kits. The good thing, what works for us, if we have a tower, basically the tower, because of its massive size, is going to take in well-grounded tower environment, the tower will take in the range of 60 to 70% of the current down. Because if you take a look at monopole or three-legged tower, then we've got the J bolts which are holding everything into the foundation, then we've got the rebar inside that, very well connected. So that tower is going to be the best conductor we might have. The question is, what are we going to do to enhance that in the soil around the tower? And I've got some slide to show you later on. So anyway, let's assume 100 kiloampere strike, which is pretty massive from what you remember looking at the distribution graph. So if we're going to have a 70 kiloamperes going down the tower, the remaining 30 kiloamperes will divide itself among all of the other service cables coming down from the antennas to the shelter. So anyway, if you take a look at the 30,000 amperes of remaining current and you take a look at a very basic tower, 3 sectors, 2 antennas per sector, 6 cables total. If you take the 30 kA and divide it into the 6 cables, basically mathematically you're going to be looking at probably around 5 kiloamperes per cable. And let's remember that around 70% of the 60 to 70% of the current will be going on the shield. Around 30% of that current is going to be going on the center pin. So you can figure out pretty much quickly how this stuff is going to divide itself. So people ask, why do we have to take a perfectly good coax cable, strip the insulation on it, apply the grounding kit, and tie it to the tower? That's basically the reason for it is the differential inductive voltage drop on the tower due to its inductance and the coaxial grounding kits. We don't want to burn insulation, we don't want to arc from cable to cable, we don't want to arc from cable to tower or cable tray. So the reason why we are really butchering perfectly good coaxial cables is just to bring the inductive voltage drop across the tower closer to the inductive voltage drop across the cable. So the rule of thumb is basically do them every 75 feet. Many people follow this format, many do not. So whatever we are doing, let's try to make sure that we are avoiding a very sharp bend, because you don't want to add any more impedance or inductance into anything hanging above the ground. So always remember that the radius, forgiving radius, is always the best way to go. And there was a question from someone basically, well, if I have the lightning diverter right here, Ben Franklin rod, sitting on the top of the tower, do I have to have that green wire coming all the way down? I've been fighting with that whole thing for for as long as I remember. If you take a look at the 250 MCM insulated wire going to the ring ground around the tower and so on, and if you take a look at the massive leg or the massive monopole being right next to it, that wire doesn't do very much. And my question was always, so if you are running a green, yellow, or green insulated wire or bare copper wire on the side of the tower, is that Ben Franklin rod insulated and isolated electrically and mechanically from the tower? No, it isn't. It is just bolted right onto the tower. I say, well, so what's the purpose behind it? As I keep telling people, does it help you? No. Does it hurt you? No. So if your local inspectors and so on believe in that whole thing, let's leave it there to keep a peace and quiet. But I would rather take the money, basically, and put that copper underground in form of radials to move the step potential rise away from the tower if I have the real estate, and basically roll it this way as opposed to rolling into the shelter and into the equipment. So here, remember when we were talking about the rolling ball theory, that's the electromagnetic field, kind of coming down in form of that step leader. And then once when you are going to have the current flow, you are going to have basically the outskirts of that whole imaginary ball, whatever it touches is going to be a subject to a current detachment point or attachment point and a discharge. So when we are modeling, the radius is going to be directly proportional to the amount of current and charge associated with that step leader and with the event, the peak current as we described in the previous statistical graph. So all we are doing right here, we are by extending the tower height, okay, we are trying to put the side-mounted antennas into that so-called protected zone. And if you take a look at the Ben Franklin rod or the lightning diverter rod, it's very sharp on the tip. There is a reason for it. You want to build the corona, okay, to start that streamer going right on the top of that guy, as opposed to having the corona being launched from the side, from the panel antenna or any type antenna on the tower, from any other sharp object. So the reason for that sharp Ben Franklin rod is to basically start streamer flowing this way. So as the step leader comes down, you are basically looking at current flowing through the tower, not through the antennas and coaxial cables into the equipment. Okay, well, there are some questions pertaining to tower grounding. By far, many people, I always keep saying that excellent, good RF ground is going to make for an excellent AC/DC ground. Seldom is it the other way around. So in most cases, what you'll see these days, basically, if you've got a 3-leg tower, you're going to have a ring around each leg, basically, with the 3 grounding rods 120 degrees apart. So basically, you are not helping to move the step potential rise anywhere. So if that was up to me, basically, I would rather take a 3 radials or 4 radials, whatever the real estate will allow you for, and run them and then go with the grounding rods from each one of them. Don't make the radials too long, because they're going to present also, even though they're going to be buried in the soil, conductive soil somewhat, they will be basically subject to impedance as well. And there is going to be some point of diminishing energy which won't be able to overcome the length of the radial. So the best way to ground the tower, and that's the first place I advise people to start with, is to create a system of radials and grounding rods, basically, to take the step potential rise as the current keeps coming down away from the shelter. We still will have enough energy coming down with the coaxial cables, basically, to the bulkhead, but the more we direct where we want it to go, the less we are going to see where we don't want to see it coming. So if you read that whole text, basically, we have to take a totally different look at the grounding for RF as opposed to grounding for AC/DC. You might drive one ground rod, hit the water table, basically, and you're going to measure half an ohm. Well, that's great AC or DC ground, but when you take a look, basically, at the dissipation capability of rod like that, it's not going to help us very much in lightning event. The most basic grounding material will be a grounding rod, and as you see, the most effective will be just the surroundings of the grounding rod, where you're going to be shunting the energy basically to the clumps of soil. And in this case, we are showing, nice homogeneous type soil, so the whole ground rod is deployed effectively. But very seldom do you have a homogeneous soil. Homogeneous meaning that all the layers over the 2 meter of the length of the grounding rod is identical, okay? So you've got the shunting capabilities straight across that rod. Very frequently we are going to have a layer. We're going to have some top layer, we're going to have a clay, we're going to have sand, we might have whatever. And the basically conductivity of that soil is going to vary basically with the number of conductive ions being washed and the composition of material, of acidity of the soil. So sometimes we will treat that material. There is a good thing called bentonite. Many of you might have heard about this material. It's very environmentally neutral powder basically, which forms a brick, like a brick around the grounding rod or radial basically. And I'm advising people to do it when they are on the mountaintop. When you've got a granite or when you've got a solid rock, it doesn't matter how deep you go, okay? It's not going to get any better. So let's form the radial, excavate the topsoil, surround it with the bentonite. It just seals very nicely at this point, and it's not only great conductor, and it's going to give you grounding performance throughout the whole year, being almost identical, but it is also protecting the copper from corrosion, basically. If you're going to have a fairly acidic soil, then the copper is going to get eaten pretty quickly down there. So we've used that bentonite to enhance it on challenging sites when it comes to grounding. This thing is going to last forever. Okay, so as you see, we started coming down from the top of the tower. We furnished grounding jumpers. In this example, one is right below the antenna. Another one is going to be when we transition RF feeder from the vertical to the horizontal. There is the cable tray. One thing before I forget, if you are grounding cable tray directly to the tower, okay, if you are bonding the end of the cable tray directly to the tower, please do not bond it to the master ground bar on the outside of the shelter or cabinet. You don't want to bring any more current into the shelter than you have to, or the grounding system for the site. So in most cases, people will be bonding basically the cable tray to the tower at this point, and they will be floating basically part of the cable tray right here. So the cable tray is only connected to one point of the structure. And if you see, what we want to make sure as we come to the bulkhead right into the equipment shelter, the rule of thumb is we want to make sure that there is no conductive flooring in that shelter or the cabinet or whatever, because you don't want the current from the shields dump onto the connectors to the filters and the grounding to just return itself, come from the top, return itself from the bottom. So the rule of thumb in this grounding scheme and bonding scheme and shielding scheme basically is going to be, if you come with your RF high, which most sites will have, ground all the cabinets, ground all the racks and everything high to the same point basically where you have grounded your RF. And make sure that this area is not conductive. If you've got a rise floor of some sort with a grid or whatever, which might be tied to the building steel, you might have some potential for current sneaking the other way and returning itself if it sees lower impedance on the return here than it would see here. Well, there was a question about the high-rise. And if you take a look, there is, by the way, I asked Lisa to make this presentation public for all of you on the Alliance website, so if you will need any references, you can always go to this one, download it, and kind of refresh some of the information. If you are dealing with the high-rise building, they are going to be populated not only with structural lighting protection system, bunch of spikes hanging around, which is tied to the structural steel of the building, or it's going to have a vertical radials coming down if this is a brick building, for example, and you're going to have a penthouse, you might have a higher tower, you might have a lot of point-to-point, multi-point antennas on small masts sitting back there tied directly to the overall structural lighting protection system. I kind of want to make it fairly short. Marginal will be bond to structural protection or separate down conductor. That will be the marginal grounding for towers, antennas, and infrastructure on the top of the high-rise. Good will be bond to structural protection and additional separate down conductor. So if you have a structural protection, that would be better than anything else. Better will be single bond to structural steel. If you take a look at how at how the steel, how the structural steel, how the newer buildings are constructed, you are going to have a knockout all over the place, because every secondary site of the AC transformer, step-down transformer, or UPS, or whatever, you have to ground the neutral, basically. So you are going to have a lot of provision in the steel buildings to make a knockout, tie all your grounding for RF, DC, AC, all the supply, all the I/O ports tied to that. And that building is going to be looking like a huge capacitor to the lighting discharge. You're going to charge it and you're going to bleed it very, very fast. There was also a question about, hey, can I use the cold water pipe? Well, yeah, if you are certain that there are no plastic pieces interconnecting some of the copper, or if you are sure that the plastic pieces won't be added down the line due to the modification of the cold water pipes and so on. So, well, it is always good to have the redundancy. Cold water pipe is good, but basically as long as you have got the total metallic cold water pipe and you are pretty sure that it is in very conductive surroundings. But in addition to this, I would advise to run additional redundant ground system, just in case somebody will have to cut a piece of broken pipe, metal pipe, and fit it with the PVC. Well, for all the guys who are working in the wireless broadband, all the 2.4, 5.2, 5.8 aspects of the business, here is an example how to protect the ODU and IDU. If you have a basically antenna, your microwave antenna and IF module incorporated in the ODU, and you are running coaxial type cables from ODU to IDU, you need to fit protection right at the base of the antenna and right in front of the indoor unit. Yeah, I'm showing this based on the coax cable. More and more RJ45s and Cat5/6 cables are going up 100 feet, 200 feet on the tower. If somebody told me 10, 15 years ago that I'm going to see RJ45 protector and Cat5 standard applied to the outside, which was developed only for in-building application, I wouldn't believe them. Now the weakest link in the whole darn thing is the RJ45 female part. You just pump 800 amperes through it and it totally disintegrates the female connectors in that RJ45. But well, I guess cheap is good, so here we go. You can imagine if you had a Cat5 basically coming down, or Cat6 connecting ODU and IDU, it will be prudent to apply some sort of a protector basically at this stage, and also one at the IDU, at least one at the IDU location. Here is an example of separation between antenna and ODU. You are going to have some sort of a piece of coax connecting your microwave right into the IF module or IDU, ODU. So it would be prudent to protect it right here. If you've got coaxial cable, protection here and here. If you have got Cat5 cable or Cat6 cable, protector here and protector there. So that's for the IP guys basically who are working in the point-to-point, point-to-multipoint wireless broadband. Well, now we are getting to the funny part of this whole presentation. If you take a look what we do, here is the massive tower leg, all the J-bolts right here, which are buried in concrete in a U-fer, and concrete, if it's moist, is going to be a relatively good conductor. And then we are running that one piece of fuse, hoping that all that current, which we're going to strip from the tower leg, is going to go on this conductor. This guy is fed and happy. He's just sitting doing nothing all day long. Coaxial grounding kits. If you take a look at the coaxial grounding kits, the fact that the kit came with the 2 meters worth of wire doesn't mean that we have to utilize this whole wire, okay? Cut them short, cut down on the impedance and inductance of that grounding kits. That's how you are removing basically the current from the shields. And this is not even that bad, what we are looking right here, where they utilize the whole length of the grounding kit. I have seen them nicely wrapped in tight coil, basically with a plastic tie hanging happy on the side of the tower, providing huge impedance and more inductance for stripping of that current from the coaxial shield. So here is a bit of a nonsense right here, but we always do it this way, right? We put a ring around each tower leg, 3 grounding rods, and that step potential rise is going to be sitting right here at the tower leg, instead of taking nice radios and running this from each leg, you know, away. Well, here is an example. This is not too good picture. I apologize, guys, for it, but somebody has decided to put, probably that looks like 250 MCM, or tough to say. I didn't get a description of the type of wire. And they have decided to put the ground lock for the tower leg very high, And here is a little grounding rod, okay? So they wanted to make sure that they divert the current from the tower leg, and it's going to go to that one grounding rod. If you take a look at the, when we had that current flow, basically, you develop a huge potential right across that piece of wire because of the fairly high impedance on the return to the grounding rod. And if you take a look, that current has decided not to go where they wanted it to go. That current has decided to flash over into the uther, into the J-board, into the foundation, into the metal reinforcing steel right inside that that footing right here. So what we are trying to protect that concrete with by applying that wire basically hurt that concrete. So it looks like the impedance of that uther and the impedance of that whole structure was much lower than the impedance of that wire and that ground rod right here, and basically have a flashover point, huge E-field build up, and I said, don't want to go this way, boom, and it took big chunks of the concrete right here. That's kind of like oxymoron. What we are trying to protect from actually happened. Well, take a look. Typical way of doing bulkheads these days. Very traditional way. You've got all the coaxial grounding kits coming. You put coaxial feeders coming in. We've got the grounding kits on coaxial cables. We dump all that current from the shields, and this is the last point where we can defend ourselves. Right behind that wall, you've got equipment, and we are dumping all that current from the shields of coaxial cables on that one master ground bar, and we put that little fuse. So this, if that current is going to be collected right here, that wire is going to have a relatively high impedance. Guess what? There is going to be a horse race between, do I want to go this way or that way? And if you are lucky to maintain this one, at least you've got some sort of a grounding for the coax feeds. Many people are not so lucky with all the copper theft going on around. They are just ripping the sides as quickly as they possibly can. And let's see, another example of copper theft and fix. So over the years, you know, being at the old place, at the old company, we came up with a little concept. Look at this as a concept. I want this event to be totally non-commercial by nature. So look at this from the engineering value-added point of view. If we did it this way, that's how the bulkhead would look like. You've got a coaxial cables, last hanger right here. You just basically enter that bulkhead at 30 degrees, so you've got a natural water drip line, and also you've got a service loop. So this way, you know, if somebody has forgotten to leave a service loop on the coax cable, especially with the large heliacs and cables like that, and you've got a shag and vibe, you know, you've got a wind loading on the tower, very frequently you would see that bulkhead, traditional bulkhead being pulled away from the shelter, and you've got all the rodents, you know, and other animals trying to get and find a shelter inside. So in this case, you've got entries for coaxial cables. You can bring wave guides. You can bring, there is a room left for wave guides, for fiber, for DC, for whatever you might have additional services. So that's the typical traditional method. That's what we are proposing. Could be a very good, viable method. And you might be asking, Bogi, where is the master ground on the outside? Well, we don't have it on the outside. Why encouraging somebody to steal it if we have other better options for grounding? And if you take a look at the traditional method, trapeze with all the protectors mounted on it, internal master ground bar right here, and another piece of ground wire going to the ring ground around the shelter. If you take a look at the internally at the proposed solutions, the cables come here. You do natural transition, high for the jumpers. You put a feed-through protectors, or you put a blank plug if you don't have enough feeders, or you can put a feed-through for people who hate lightning protectors. You can put basically a feed-through connectors, and you are capturing all your ground. No grounding kits on the outside. You've got a nice, beautiful flattened bulkhead mount for all the protectors, and then you've got an adjustable plate right here, an 18-inch wide plate. You tie a couple of 2-odd wires, basically short pigtails, go through the shelter, and you cut weld them to the outside of the ring. You are done, nothing to steal. And if you came to me and said, hey, Bogi, I need a 25-volt protector, okay? If I put this protector, you see the traces right here, 25 volts on the positive side. If I put this protector here, you get that 25 volts. If I put the same protector right here and add 1.5 to 2 feet of wire, the 25-volt protector will become more like a 700-volt peak-to-peak protector. The best hidden secret of the industry, okay? Let's not talk about the lead length. So here how that looks like, basically loaded, and the accessories, optional accessories to it. Here is another marketing picture. You can adjust that plate to the different wall thickness, anywhere from 4 to 8 inches master ground bar for grounding all the rack equipment, and everything comes in. So we call this a single point by design, not by installation. Much less expensive way of doing business than going with all the components of the traditional method. And here is the area where we can cut out holes, basically put the weather seals and bring any other services and protect any other I/O ports and ground them right here to the panel or to this grounding bar. Here is a picture of the installed one. Another picture of that panel sitting on the cabinet. There's a good example. Guy called me. He had a water tank basically. He had some antennas mounted. He was using a LMR 600 cable. Said, Bogey, every time he was from Carolina, North Carolina. Every time I've got a lightning storm, I keep losing these channel banks. And so he sent me this picture, and as you see, a couple of LMR 600 coming here. Here are protectors installed, and here are jumpers. The protectors are not grounded at all. They are sitting very, very happy. They are not being bothered by anything, and the guy keeps blowing his channel bank. So I said, hey, we're going to do a very inexpensive fix. Go to the Home Depot, get yourself a piece of copper, a piece of aluminum, ground this. We added a very nice strap. I also advised him to capture. He didn't have a grounding kits on the water tower at all. He didn't have a grounding kits for the coax shields as they came into the building. So basically we fixed it. I haven't heard from him since then. So I'm assuming it works. But, you know, you'll see that. Yeah. You know, there is no way any type protector, regardless how much money you spend, is going to work for you if you don't take good care of grounding first. And as we say, if everything else fails, there is always that guy. And every guy, everybody has got some sort of a handy plastic tie. And just for laughter's sake, this was taken from the actual site. Now we are getting to protectors. The basic function of every protector, regardless if this is data, PoE, RF, AC, DC, whatever you are using, the basic function of that protector is to be able to withstand given amount of current and control the differential voltage between center pin, or minimize the differential voltage between the center pin and the shield and local ground. So if you take a look, basic parameters for RF will be basically the return loss. Here is one from 20 meg up to 1 gig. Once again, I'm not selling protectors. I'm just basically sorry, my mic was goofing with me. Just basically when you are selecting them, you've got to make sure that they're going to look fairly transparent to your RF. You don't want to have any issues with insertion loss, with the return loss, so they should be pretty transparent and come only online when needed. So pay attention to the RF characteristics and then the surge protection characteristic of every unit. PIM. Many of you who are bothered with PIM, if you are or affected by PIM, make sure that the manufacturer who is supplying you with the PIM-rated devices is testing them 100%. When I was with the other company, I mentioned, you know, PIM was a scary issue. We came up with a brilliant line of PIM protectors, basically, and you see some of the performance levels. But demand certificate and demand that the protector you are buying, if there is a PIM rating issue, demand that they are certified to PIM or 100% PIM tested. Here is an example of a protector where they promote or advertise better than 155 dBc, and actually that poor guy is barely making 123. And it's also important to remember that when you do PIM, you are basically doing static and dynamic PIM testing, or manufacturer does static or dynamic. Here is an example of how to minimize the number of connectors. Here is a device going up to 6 gig. It is a basic gas tube, you know, but anyway, it's bidirectional. And you can basically, that could be crimped directly at the end of the cable using the same CST 400 tools for the LMR 400. So you basically eliminate 2 connectors for protector. You can crimp that, you know, basically at the end of the coax cable, and there you go. Surge testing. It is very important if manufacturer provides you with the data that the current, this is the current trace, and you are looking right now basically at 6.4, so that would be like 3,200 amperes going into the device, and this is the corresponding voltage. So as I said, every protector has to be designed to withstand given amount of current which is advertised to, and hold the voltage, differential voltage between the center pin. This is for the GPS protector. Here is one which goes from 2 to 6 gigahertz. GPS has to make a provision for 5 volts bias voltage basically to power it up. That's why you see the protection level of 12 volts factoring that 5, 6 volts. If you are doing a high band pass filter protector basically, you don't have the DC bias at all. So if you shoot 3,200 amperes, you can limit the voltage to less than 2 volts peak. So there are many different RF protection topologies. There was a question, how do I know that my protector is good or bad? And you know, guys, I'm always saying, hey, you're going to know, the protector will let you know. You're going to see a hit on some reflected power, you know, if the protector is going to change its impedance from 50 ohms to whatever, if it's going to go through deterioration. You're going to have some reflected power issues, some noise issues, you're going to have visual issue, you're going to have some insertion loss issue, and basically you go, replace it, or sweep it, and you know exactly, no, but we want to really know if it's good or bad. So after just debating that for a number of years, we came up with a little handheld tester, basically. This is kind of a prototype picture. Right now, we're going to be launching that very soon. We're going to have a couple of N connectors, female and male, and we're also going to come up with a little alligator clips, you know, 2 clips with the N interface, which you could use to test varistors or data line protectors or anything with different terminals than RF terminals. And basically, you turn the power on switch here, you depress the test button. We're going to be launching around 1,000 volts at roughly 1 milliamperes. We could go to 2,000 volts, but I was kind of a concern about the safety, and most protectors will be below 1,000 volts anyway. So I have decided basically to launch that thing. You test, and the digital display right here, this is just the cover face. You're going to have a 4-digit display, which is going to read the voltage protection level. It could be used as any portable. It's going to be kind of a like fluke, like a DVM by nature. And we are getting slowly to an end of this presentation and questions and answers. I just put some useful links and contact information. I used to work with Ken Rand at Polyphaser for many years. He's with us right now, and so we would be welcome. I know that everybody's situation is going to be so unique because we've got a very diversified group of people coming from across this industry. But anyway, if you have any specific case study issues, questions issues, please don't hesitate to drop me an email or drop Ken an email, and we'll be able to help you, or I hope we'll be able to help you with your specific situation. Then I put a link to kind of a mini publication on the topics we have covered today, which could be downloaded from Times Microwave website. Then there is basically article on low PIM protectors, you know, lightning protectors and PIM, what do you need to know. Then I put another link right here for Times Protect brochure. This one was from the AGL, above ground level article. And then for all of you who are asking about the CST magic and about the active terminals and about all the witchcraft, the umbrellas hanging all over the towers with the sharp points and objects pointed out, I don't want to sound too biased. I would rather have you guys, I have the whole scientific community and people who are dealing with the phenomenon of lighting protection and grounding is just blown away that somebody can sell magic basically against a basic engineering 101, trying to horrify people who are concerned with lighting damage, who are afraid of it. That's not even funny. So I kind of, instead of covering this whole subject from the physics point of view or electrical engineering point of view, I would rather have you go to these 2 links, and you're going to have laughter. Some of you might be dismayed, you know, that whole industry flourished so much, and there are still people, you know, who kind of, you know, believe in that theory. But anyway, you'll have to use your own judgment when it comes to that. Okay, and we are right here at the, that was very quick. I realized that was extremely quick, and I spoke fast trying to give you a bit of a flavor. So at least you know, in case you are in trouble or you have some questions, specific questions, you'll know where to find us or go to some resources to read. Okay, I think I will close with that and appreciate everybody's attendance. Stay in touch if there is anything I can do.
Thanks, Bogey. It's Lisa here. I know there were a lot of questions that were answered on the registration and a couple that have just come in, but we're going to handle those by email just because, as Bogey mentioned, there's a lot of this difference between the audience and what they're interested in. So thanks again for attending, and look for a link follow-up from me with the link. We're going to be posting the recording of this presentation and a PDF. So even though you were speaking fast, they'll be able to play it over and over again.
Okay, yeah. Am I still online?
Yes, yes.
Yeah, one quick question I wanted to ask, because I kind of feel like I ignored a bit the IP guys. There was a question regarding protection of buried data cables. Well, if you build them in the PVC type settings, hopefully you're not going to run them through the metallic conduit basically because of the RF chop issues and noise issues. It is always a good idea. You're going to be sitting very close to the ground. As soon as you come out of that cable, put a protector around it very well to the local grounding source. If you have to do it on both ends of the cable, do it. If you have to do it on one, you have to keep that protector as low basically as possible.
Okay, that's great. That's great. Thanks a lot, Bogi.
Okay, thank you guys. I appreciate it.
Great. Bye-bye.
Bye-bye.